session starts with the superconductivity and correlations in nickel-based oxides. First speaker is an invited speaker, Carsten Held from Technical University Vienna, Austria, and his title is Nickel-Age Superconductors, a Renaissance of One-Band Hubbard Model.
Okay, thank you very much. And first of all, I'd like to thank the organizers for the kind invitation to come here to this wonderful place. As our chairman already said, I'm going to talk about nickel-age superconductors, a renaissance of the one-band Hubbard model. As the title already suggests, based on ab initio calculations, I will put forward a very simple picture for the physics of nickel-ages based on a one-band Hubbard model for the nickel x squared minus y squared orbital plus largely decoupled pockets. We will then see that this simple description agrees with most of the well-established experiments. I will show that later to you. But we will also have two further speakers in this first session. So Ariando will discuss on the experimental side in the next talk, and then Frank Lechermann will put forward another picture for the theory where instead of these pockets you have a nickel z squared orbital as a second orbital involved. Before I start, I'd like to thank my co-workers, and let me in particular pick out these young guys, Liangxi, Motoharu Kitatani and Paul Worm, who did most of the actual calculations. 3 years ago, we entered a new age of superconductivity with an enormous experimental and theoretical activity. So after the copper age and the iron age, we are now in the nickel age, and as you see here, the TC has started to increase. It will increase further, that I'm sure of. Whether it will ever surpass the cuprate TC, it's questionable. My motivation, however, is also not to get a room temperature superconductor out of the nickel-ages, but that these nickel-ages are at the same time very similar, but also decisively different to the cuprates. So the iron pnictides are a completely different kind of system, but the nickel-ages and the cuprates have so much similarity, but also are more different than the cuprates among themselves, so that we have high hopes that they will allow us to better discriminate the essentials from the incidentials for high temperature superconductivity, and eventually to better understand ITC. The outline of my talk is as follows. I will start with the electronic structure and the ab initio calculation, density functional theory and dynamical mean field theory, and then I will arrive at this simple minimal description with only the x squared minus y squared correlated orbital and the largely decoupled pocket, in particular the A pocket. Based on this simple description, we have then calculated the superconducting dome at a time where only two experimental data points at 20% doping were available by Harold Wang and Ariando. And we predicted the whole doping dependence when we only had 20% doping. And this prediction has now been experimentally confirmed with breathtaking accuracy, much better than we had expected. And that is thanks to new defect-free films. I will briefly discuss it. I will then also show that finite layer nickel-ages nicely match into this overall picture, and if time allows at the end, discuss how to increase TC, for example, by using pressure, strain, or palladates. All right, so if you want to understand nickel-ages, how it looks like, make a theoretical modeling, the very first thing you should do is density functional theory calculations. And indeed, such DFT calculations have been done more than 30 years ago by Vladimir Anisimov. And based on these DFT calculations, he concluded that nickel-ages are cuprate analogons, and because of that should be superconducting. Now, this theoretical prediction was extremely difficult to verify in experiment. Ariando might tell us more about that. It's very difficult to synthesize these nickel-ages, and it took 30 years before Danfeng Li and Harold Wang were able to see the superconducting transition in strontium-doped neodymium nickelate. And then people already started to doubt, get rid of oxygen and to use hydrogen for this reduction. And then it is very easily possible that you end up with excess hydrogen, as we predicted, and the Keimer group recently has nicely demonstrated, or you can also have some excess oxygen. So these films are really prone to disorder or stacking faults, and that one has to take into account. Okay, now let's go to the theoretical modeling, and let's start with the very basics. So that is the crystal structure. It's identical, the infinite layer structure, to the arguably simplest but certainly not best cuprate superconductor, calcium copper O2. Here you have the nickel oxygen 2 layer, and then you have a neodymium or other rare earth spacing layer, and this you have a neodymium or other rare earth spacing layer, and this pattern is continued or repeated ad infinitum. And therefore it's called infinite layer structure. And if you make the formal valency count, copper is 2+, nickel being to the left in the periodic table is +1, which is difficult to obtain. And then both of them have a 3D9 basic electronic configuration. So that speaks very much on similarities of these compounds. But now let's go into the details, and then we will also see differences. That is the DFT band structure of calcium copper O2 and lanthanum nickel O2. And they are quite similar, but also different in some aspects. So you see here the x squared minus y squared orbital crossing the Fermi level. It gives rise to these hole-like Fermi surfaces. Or if you go to the, it's hard to see, a red dashed or red first Brillouin zone, then you have 4 of these Fermi pocket sheets in the cuprates, as you know. Now that is the weakly interacting picture. Now if electronic correlations come into play, this x squared minus y squared orbital splits into 2 Hubbard bands. And then for the cuprates, it is such that the oxygen orbitals are closer to the Fermi level than the lower Hubbard band. And because of that, if you hole dope the cuprates, you get the holes into the oxygen. So cuprates in the Zahn and Sawatzki-Allen scheme are a charge transfer insulator. Still, a Hubbard model can be used as an effective description, but with some working around to make it, to justify it. Now, how about the nickelates? They also have this x squared minus y squared orbital. It has a very similar hole-like Fermi surface. Now, nickel is to the left in the periodic table, and because of that, this x squared minus y squared orbital is pushed higher in energy with 1 electron, and because of that, it's further away from the oxygen. And because of that, nickelates are not charge transfer insulators, so the holes should go also into this nickel x squared minus y squared orbital. But then it's also closer to the lanthanum or neodymium bands, and that you see here at this A and gamma momentum, these bands cross the Fermi level and give rise to this gamma and A electron pocket. So you have in DFT a mixture of a hole-like Fermi surface and 2 pockets that you have here. Now Frank will talk more about the Z-squared orbital that is further or lower in energy in the cuprates. In the nickelates, it's somewhat closer to the Fermi energy. Again, this was just a DFT picture, and now we have to think what correlations do as for the cuprates, where you get a charge transfer insulator. And to this end, we have done DFT plus DMFT calculations based on all nickel and all neodymium 3D and 5D orbitals. And if you can see it from the back here, what you see is first of all a strong quasi-particle renormalization. So that white lines here is a DFT band structure, and you get a renormalization by about a factor of 5. You also get some finite lifetimes, therefore you have these broadened energy levels. But you see still here that's the x squared minus y squared orbital, and you still have an A pocket. The gamma pocket, which was there without correlation is now shifted above the Fermi level for lanthanum nickelate, but for neodymium nickelate, the gamma pocket still is below the Fermi, or the gamma band crosses the Fermi level, and you have a gamma pocket. But if you strontium dope the neodymium compound, also this gamma level shifts up. And because of that, you see here in some compounds, at some dopings, you have the gamma pocket, in others you don't. And because of that, we think it is not relevant for high temperature superconductivity in these systems. So here is, by the way, the Z squared orbital, still below the Fermi energy. And let's now, based on these ab initio calculations with all d orbitals included, get at a simple description. And the simple description is, okay, I have this x squared minus y squared orbital, an A pocket, in some compounds at low doping, possibly also a gamma pocket. But these two are there all the time, also in the superconducting regime. So these are the relevant orbitals in our calculation. And let's use Occam's razor now and make the simplest possible description for the nickelates, and that is just using these two orbitals. It becomes even more simple, because these are these two orbitals, the x squared minus y squared orbital in the nickel oxygen 2 plane, and the neodymium xy orbital. And these two orbitals by symmetry don't hybridize. So there's no hopping of electrons, between these two orbitals. And therefore, as a first approximation, we can consider these two orbitals to be decoupled. Still, if they are decoupled, this A pocket plays a role, because if you strontium dope your system, you put holes into your system. And now part of the holes will go here, and part of the holes will go there. And therefore, one has to carefully consider how many holes are going into this x squared minus y squared orbital or Hubbard band, and how many go to this decoupled xy orbital or A pocket. We have calculated this fraction that's shown here. On the right-hand side, for the blue curve, you see the occupation of this x squared minus y squared orbital. And here you see the strontium doping, here for neodymium nickel O2. And you see even at 0% strontium doping, you have already about 5% holes in your x squared minus y squared orbital. That is because you have electron pockets, so some of the electrons are moved away from the x squared minus y squared orbital and are instead in these pockets. And that also nicely explains why there is no long-range antiferromagnetism in the nickelates, in contrast to the cuprates, where for the parent compound you always have antiferromagnetic long-range order. If you have a 5% cuprate, 5% whole dope cuprate, you wouldn't expect long-range antiferromagnetism either. Now, if you strontium dope the system, some of the holes go here, some go here, and if you look at the slope, it's about 50-50. 50% of the holes, roughly speaking, go to the reservoir, 50% to the Hubbard model. We have then calculated from ab initio all the interaction and hopping parameters for this one-band Hubbard model, and this translation of strontium doping to the occupation of the x squared minus y squared orbital we still need. Okay. So that is our description, and then I will continue with that. But let me also point out that at larger doping, this Z squared orbital becomes then occupied or deoccupied, so occupied with holes, depopulated with electrons, and therefore you have this change of slope here for larger doping. There are quite a number of other theories for the nickelate. So at the beginning, people were very much excited when you only had neodymium nickelate, that wow, now you have an F electron superconductor, and people thought it is relevant. So we calculated the Kondo temperature. It is so low that it doesn't play a role. And therefore, we didn't think the Fs are relevant. Of course, you still have some spin scatterers, but they are not so strongly coupled because you have a very weak hybridization. And then it has been experimentally also ruled out by finding superconductivity also in other compounds like lanthanum nickelate, where you don't have F electrons. And then Frank later will put on a picture on the relevance of the Z-squared orbital. And there are indeed two schools of thinking for the Z-squared orbital. One is here's the groups of Haule and Philipp Werner, where you have in particular this gamma pocket relevant for the Z-squared orbital. I told you that the gamma pocket is a neodymium or lanthanum derived orbital, but it has a strong hybridization with a nickel Z-squared. And because of that, you have something like 15 or 20% holes in your original nickel Z-squared orbital. This gamma pocket is not strongly correlated, and as I've shown you before, our point of view is that this physics, where you can maybe then have this 15-20% doped Z-squared orbital and its spin coupled to the X squared minus Y squared orbital, we think that can be relevant physics for lowly doped neodymium nickelate, but since this gamma pocket is so different among different compounds and doping, we don't think it's the relevant point for superconductivity. And there's a second theory by Frank Lechermann, and as he nicely showed, the difference comes about just by using thick density functional theory instead of density functional theory. And there you get rid of this A pocket, and instead this Z-squared Fermi surface is present for any doping of the system. That is similar as in our calculation for larger doping. We get similar physics, but only for 25 or 30% doping. Okay, that is what I wanted to say about the modeling and arriving at this one-band description. Maybe I should also point out, but that is very indirect evidence that interpretation of Rick's data suggests that mainly the X squared minus Y squared orbital is contributing to the Rick spectrum, but it's not a direct proof. Okay, so now that is our picture, only these two ingredients, and let's see how far we come with it. So we can now calculate superconductivity. There has been in recent years quite some developing extending dynamical mean field theory. There's a review on that also. And we used to this dynamical vertex approximation, d gamma A. And what you can describe here is, among other, spin fluctuations. You all know spin fluctuations from RPA at weak coupling, but now we have in these vertices gamma, we have included all the local DMFT correlations already. And because of that, we can now describe spin fluctuations also at strong coupling. There's a nice paper by Thomas Schäfer and others showing that these spin fluctuations calculated are in excellent agreement with numerical Monte Carlo results. Indeed, it was such that first the Monte Carlo results differed, but then they did a better finite size scaling, and now they agree with the d gamma A calculation. Now these spin fluctuations act we also treat charge fluctuations on an equal footing, but we find here predominant antiferromagnetic spin fluctuations, and these spin fluctuations act as a pairing glue between two electrons in the Cooper channel. In this way, give rise to superconductivity. So the method is not biased. We can get S or P or D wave superconductivity, but for this calculation here, we get D wave superconductivity mediated by antiferromagnetic spin fluctuations. Okay, let's now look how things are. The first thing these spin fluctuations modify is your one particle spectrum or your Fermi surface, and that is shown here. Remember 5% doping, that was the parent compound, and only shown here is now the X squared minus Y squared orbital. And for the parent compound, you see, similar as for the cuprates here, a pseudo gap in the spectrum. Now that is the superconducting doping regime where you have nicely pronounced Fermi surfaces. Okay, and next we can calculate superconductivity this way. It's a superconducting TC as a function of strontium doping, and remember we had to translate the doping to the actual filling of our x squared minus y squared orbital, which is shown up here. That is how it looks like. In this dark blue regime, we think this one-band description is sufficient. We also have an A pocket, but it's decoupled, and the x squared minus y squared, orbital is the correlated one, which we think is responsible for superconductivity. Now here, at low doping, you can have an additional gamma pocket. The physics can be slightly different. Here at large doping, we get also a different physics, because then the z-squared orbital makes an other Fermi surface. And that is the calculated TC at a time where there was only 1 or 2 data points at 20% doping available. So this data point. There are no free parameters, and the agreement for such a difficult to calculate quantity as a superconducting TC is quite good. Yeah? And then further experiments came, and first in 2020, also by Ariando, but I put here all the data from the same group in Stanford, and you see a superconducting dome. Now here the agreement is still, with the disagreement you had at the beginning, that is what you expected, and of course people were asking us, what are you doing wrong here, and we don't feed back the superconducting fluctuations to the antiferromagnetic fluctuation. Therefore, we don't get, for example, a Kostelet-Thouless transition that overestimates TC a little bit. So it could have been that it's like that. But then just this year, new experiments with clean film came out, and they gave this TC. So all we did here is we put these films with the strontium doping onto our phase diagram. And that is really in breathtaking agreement. And the difference to the cuprates is that the regime is larger, yeah, but it's only larger as a function of strontium doping. If you go to as a function of the doping of your x squared minus y squared orbital, you have something like 12 to 22%. That is similar to the cuprates. Then you have also a little bit skewness in the superconducting dome compared to the cuprate, and that is because you have no linear scale here in this doping regime. So all of that is nicely explained. Now, why are these films much better? So the old films had these Rudels and Popper stacking faults, so there's a lot of disorder, and the new films don't have this disorder. And this way, the resistivity dropped by a factor of 3, and the TC was also enhanced by, depending very much on the doping, a factor of 4 or 2 or whatever. So you see here, cleaner films are now in excellent agreement with our theory. These films are grown on LSAT instead of STO, but you see here within 1% the lattice parameters are the same, and that is all what enters in our calculation. Okay, that was the superconducting TC. It's driven by antiferromagnetic fluctuations, so let's compare the antiferromagnetic fluctuations to experiment. We can compare to RIX. That is our paramagnon spectrum, so energy momentum resolved, and that is the paramagnon excitation in theory, and that is the experiment. So again, no parameter fitting, it is just our old data, and we now also calculated the paramagnon spectrum. Here you see the maxima of the experiment in red, in theory in blue, and it is giving a very reasonable agreement. So the experiment is a little bit lower. That means the antiferromagnetic exchange, J, is a little bit lower. But remember, it's still here the films with stacking faults. So if you have disorder, our understanding of doing a lot of calculation, which I'm not having time today to show with hydrogen, excess hydrogen, is that then you have also at least locally some ferromagnetic exchange, some disorder in the exchange, and then you should expect such a difference here. And we would now predict that the cleaner films will then end up somewhere in between our theory and the old experiment. Okay, so that gives overall a nice agreement. Let's briefly go to the infinite layer, from the infinite to the finite layer compound. So Giulia Mundi has grown these 5-layer nickelates with 1, 2, 3, 4, 5 nickels, then a Rudolphin-Poppe spacing layer, and then another 5 layers. As you see here, the hopping parameters are virtually the same. That's very different from the cuprates because it's not bulk systems. All of this has been grown on a strontium titanate substrate. And because of that, the 5-layer system is very much alike. But of course, the 5-layer system now has, oops, that wasn't me, okay. Thanks. But of course, the 5-layer system now has 5 surfaces. In DFT, you still have pockets. In DMFT, the pockets are gone. And as the pockets are gone, if you have these 5-layer films, you can do the algebra, then you have a filling of 1/4 or 20%. So now let's put this data point of the 5-layer film into our phase diagram, and it's 20% doping. You have 3 inequivalent layers, therefore you have a little bit of variance in the doping of the 3 layers, but it's not much. And this data point is nicely in agreement with previous experiments as well as the D gamma A calculation. Let me also point out that the 5-layer compound has a positive Hall coefficient. And that is, of course, clear if you have no pockets, no electron pockets, you only have the Hall-like x squared minus y squared orbital, and that gives rise to a positive Hall coefficient. Whereas for the infinite layer compound with the pockets, it's small doping, you have negative Hall coefficients, which one would also expect from the theoretical calculation. Okay, so let me just briefly say that how to increase TC. We see that one should have a lower Coulomb interaction to hopping ratio. That is possible by using, for example, pressure, and that has been spectacularly confirmed experimentally that at 12 gigapascal you have the nickelate superconductors with the largest TC of 30 Kelvin nowadays. So that matches, and with this I come to my conclusion. So I have put forward a very simple description. There are other descriptions just based on a Hubbard model and a reservoir. And our firm belief is that this Hubbard model description is even more justified than for the cuprates. And then I've shown you the phase diagram and the excellent prediction of the experiment. And okay, just for the discussion, so I've put forward here experiment, our theory, and then Frank will put forward the x squared minus y squared plus z squared theory. And here is a little bit of an overview what we can describe and not. And I think, do I still have time to go through it? Or? Yeah, okay. So we have of course, Frank can maybe put in some question marks here and tell us what it's doing. So why, so first of all, we have ab initio derived this kind of picture. Frank has another picture because he uses SIG DFT as a starting point. And then it's, of course, difficult to say which of the different theories, which are very different, is correct. So we have actually predicted the phase diagram. And I have to say, you're getting such high TCs as you have in the nickelates. It's maybe small compared to the cuprates. But most of the time, a D gamma A calculation gives you essentially 0 for TC. So it's very difficult to have a situation, a band structure with TCs of 15 or 30 Kelvin. And we predicted the phase diagram with astonishing accuracy. I already briefly mentioned the Hall coefficient, so at least the tendency is that it is positive for the 5-layer, and it is negative and only turns positive at low temperature and high doping for the infinite layer compound is what one would qualitatively expect these tendencies, but we didn't do a calculation yet. Then we get antiferromagnetic spin fluctuations, and well, Ariando will tell us maybe more about different kind of spin fluctuation. There's also spin glass behavior. You also have some ferromagnetism seen in the system. So our point of view is that this spin glass in ferromagnetism is due to disorder in the system, excess hydrogen or oxygen, but antiferromagnetism has been firmly established in many experiments indeed. The self-doping of the nickel band nicely explains why it's only fluctuations and not long-range order. And then there is quite some discussion about the gap. So we clearly have a D wave, Frank also gets S wave, and in experiments there is also different experiment even based on the London penetration depths. Ariando and the group of Harold Wang arrive at different conclusions there. Then there is no RPES. So RPES would be, of course, a good way to discriminate between different theories. There is a photoemission spectrum, but that is, in my view, a little bit suspicious because there is no density of states even for the doped compound, which is clearly a metal, which is getting superconducting, and therefore, so we are for sure in disagreement with this photoemission spectrum and the rigs I already mentioned. So with this overview, I would like to thank you for your attention, and we will have, I guess, a vivid discussion with different theories and experiments now.
Thank you.
Yes, I have. Okay. I have two questions possibly related. I mean, one is I just didn't catch how you parameterize the superconducting scattering in your calculation. What is the input which gives the superconductivity? That is number one. And the other is, I do not, also maybe you said, but this DMFT component in your calculation, is it only shifting away those pockets which you do not see in experiment, or is it actually doing something for the superconducting calculation?
Okay. Okay. So first of all, so we didn't put in any scattering by hand. So we derived from DFT and DMFT at this simple description with x squared minus y squared orbital and an A pocket. We then calculated how many holes go to the x squared minus y squared orbital, and then we calculate the TC of this simple Hubbard model by using dynamical vertex approximation. What you get, and what was maybe a little bit short in the explanation, is we get charge fluctuations and spin fluctuations, but here we find spin fluctuations to prevail. That is because you have these kind of Fermi surfaces and close to half filling, a little bit doped, and there we just find dominant spin fluctuation. We calculate the susceptibility, the vertex of the spin fluctuation, and the vertex of the spin fluctuation then enter the Cooper channel between the electrons, and that gives rise to superconductivity. So there's nothing put in. We derived everything, as I have explained, from DFT and DMFT. Yeah, which we calculated by CRPA. And could you repeat the second question?
MFT, does it do something just to shift the pocket, or does it do something to the superconductivity?
So DMFT has no D-wave superconductivity. To describe that, we have to go beyond DMFT. Walter is also an expert on that, so we have to use these extensions of DMFT. So from the DMFT calculation in our, we just get the vertices, local vertices. If you connect these local vertices by local green function, you get the DMFT self-energy. But if you do now non-local green functions, then we get antiferromagnetic spin fluctuations among others. And we see here these antiferromagnetic spin fluctuations dominate. Now, what DMFT does compared to DMFT and what DMFT does compared to DFT is that you get some renormalization, yeah? But the main effect is, as you said, I'm not used to this laser pointer, sorry. So you get, so the DFT bands are like that, and then you get a quasi-particle renormalization by a factor of 5, and this quasi-particle renormalization enters in this vertex, and from this vertex you can then reconstruct also this DMFT kind of bands. So you get lifetime effects, yeah, that is relevant, but the spin fluctuation scattering to the lifetime is not included in DMFT. There you need to do this d gamma A to get this pseudo-gap phase where additional spin scattering gives rise to opening of a pseudo-gap. Yeah? But as you say here, or see, you get some shift of the gamma pocket, but already in DFT it is strongly dependent on the compound and the doping.
We are behind schedule, but we have one more question. So we try to keep short.
Okay, first of all, I find this really impressive. Congratulations. My question is, the TC you compute, I guess it's something like a pair formation temperature. Don't know how exact.
Yeah, indirectly it might be possible, but what we do is we take the spin fluctuation, we go to the particle-particle channel, but we don't put the particle-particle fluctuations back. And because of that, we get a mean field kind of description for the superconducting TC and not a Kosterlitz-Saulus transition. So whether if you do it self-consistently, you get a Kosterlitz-Saulus transition needs to be seen. Because of that, we get this mean field and not Kosterlitz-Saulus transition. But for experiment, it's also much closer to experiment. We have learned yesterday how large systems you need to really see a Kosterlitz-Saulus transition, and also since you have the coupling between the layers, so your correlation length becomes exponentially large, and then you easily order, even if the interlayer coupling is very weak. So far it's STM experiment and London penetration depth interpretation, but I guess this is a good transfer to the next talk. Maybe experiment is going to measure in the future such phase dependencies. Thank you.
Our next talk is also an invited talk, superconductivity in infinite layered nickelates. Ariando from National University of Singapore.
Right. So good morning, everyone. Well, actually, I can just jump directly to my conclusions now because everything has been said by Carsten. Anyway, so maybe it's still good for those who didn't follow this history of the nickelates. So I can still start with very basic things. So I'm going to talk. Well, maybe I like to make a disclaimer first about my name because Carsten keeps saying Ariando. just to be clear, I have a single name, Ariando. I mean, formally. So this is quite common in our country. So nothing illegal about that. But because of difficulty traveling, and also with a scientific community, so I create this name Ariando. Well, formally. So I'm going to talk today more from the experimental perspective and show some result and try to compare this with the cuprate. So let me start. I'm from National University of Singapore. Just to acknowledge the people who are doing this. So these are two of my students who really are doing this work. Well, of course, supported by many other people in the group. And our penetration depth is done by Albert Chia from Nanyang University of Technology. And we also did a high magnetic field experiments, and this is mostly done in Toulouse, and right now it's also in Los Alamos. And high resolution TM done mostly by Penny Cook initially, but now transferred to Peter in Max Planck. And millikelvin experiment done in Hong Kong by Professor Goh and his group. So I also like to acknowledge the funding agencies, National Research Foundation of Singapore, Ministry of Education, and Agency for Research and Technology, ASTAR. All right, so again, why we are doing this one, come back to this complex phase diagram of the cool plate. So we know that there are these many fluctuations surrounding the superconducting dome. So this can be possible, leading to possible different mechanisms that we still need to understand. So to help this one, the main motivations why we do the nickelate, I mean, this has been done, of course, in the last 30 years. So can we find a couplet analog to this to better understand the high TC? Right? Right. So as a guiding principle, and naively, right, we can think about this square lattice of the couplet as a starting point. And then we have this two-dimensional nature with a single orbital Hall filling. And then, of course, the antiferromagnetic ground state. So looking into this all, so nickelate has been proposed to be a promising system because, well, in principle, to get the Hall filling, you can go from you can do different orbitals, 3D7, 3D5, 3D1, but nickelate promise to have this 3D9 if you can make it nickel 1+. And this is not a stable system, so naturally you will get 2+ or 3+. So to be able to produce the nickel 1+, you have to do something, which is trying to remove the apical oxygens in the perovskite structures. Okay. So this has been proposed to be a system that can, have this all different ingredients that I mentioned before. Right. So with this, you can achieve this 3D9 orbitals. And the questions, of course, whether you can isolate these half-filling orbitals of the 3D9 in the nickel 1+. So by removing the apical oxygens, and then you will get this planar structures, right? And these planar structures, crystal field, will lead to the isolations of these z orbitals of the 3D. So leaving the xy minus y square high in energy isolated. So basically now you can fulfill all the ingredients that this copper oxide have, okay? All right, so with that in mind, in the last 30 years or so, people have been trying to do this, trying to achieve this nickel 1+, including, for example, doing super lattices, trying to induce a charge transfer to be able to come to this nickel 1+ state. And only recently, Dan Feng Li in Stanford, our one's group, that produced this superconductivity in the ND doped by strontium. So as you can see here, the TC is around, so by starting with a dope NIO, and then reduce the apical oxygens, then you go from the perovskite structures to the infinite layer structures, and then it give so the parent compound itself, after the reductions without strontium doping, has this metal insulator transitions, weak localizations at low temperature, while the dope one has this TC around between 10 to 15 degrees. All right? And well, within half years or so, we have been able to reproduce this system. Then we developed this doping dependence of this ND-based nickel superconductors. And as you can see here, so the left one is the resistivity of the perovskite structures with this metal insulator transition in the parent compound. And then as you dope, then it's become a metallic system. So as I said before, so for doping around 0.1 also to 0.25, so we have been able to produce transitions, from very low few Kelvin to 15 Kelvin transitions temperature. Right, so more or less this is what we have obtained these days. So this is different nickelate superconductors, Nd-based, lanthanum-based with strontium or calcium dopings, right? And also recently, based on this N5 of the multi-layer analogs of the infinite layer from the Rudelsen-Popper compound. So Mundis and his group, has been able to produce this superconductivity as well, as even though the TC is very, very low, it doesn't reach zero resistivity. And of course, there have been also a couple of other groups that have been able also to produce superconductivity in this nickel-based superconductor. Right, so is this new nickelate really like cuprate? So here, if we look to the 3D electron counts, when we plot the TC as a function of 3D electron counts, as you can see here, so it kind of replicate what we have in the cuprate, right? So even though within a smaller doping range, but within the same amount range of 3D electron counts that you produce as superconductivity. So this is also where this the Rudelsen-Popper compound picture comes into from this 3D electron count. As you can see, if you start with a 3-layer system, then you are still away from the dome, then you need to probably play with the dopants. While in the case of the Julias, so she did the 5 layers, and then you come directly simply based on the self-doping within the regimes of this superconducting nickelate dome. And then, well, there's, of course, this is kind of the similarity, but of course you also notice there are differences. For example, in the case of the cuprate, we have this antiferromagnetic and parent compound, while in the overdoped regime, for example, you have a metallic state. While as you can see here from the first diagram of the nickelate, in the case of Nd, so both underdoped parent compound as well as the overdope, they shows this weakly insulating behavior. So it's basically a metallic with a weak localizations at low temperature. Also, as you can see here, so this is the temperature where you have a crossover between electron and hole dominant carriers. So if you go from underdope to overdope, you have transitions between electron dominant carriers to hole dominant carriers at different temperature depending on the amount of dopants that you have, right? So as you go down, for example, for 0.2, which is kind of considered as optimally doped. So you start with the electron dominant carriers, but then around 80 or so, then you start to have whole dominant carriers in this 0.2 Nd-based system. So this change of the dominant carriers is not just as functions of dopant and temperature. We also notice as we play with the thickness of the system. So when we go from the very high thickness, high means around 10 to 15 nanometers, go down to around 4 nanometers, then you also see a crossover of the dominant carriers. So if we look to the resistivity behavior, so this is in the case of the optimally doped. So it shows this strange metal behavior linear with T dependent, like what we have also in the cuprate. But if we look into the overdose regime, so it's a bit more complicated. So within a particular regimes, I don't show it here. You can fit with a different dependence of temperature. But dominantly, as you can see here, at very low temperature, you have this upturn, which is different than what we have in the case of cuprate. All right, so I just try to relate a little bit with what people have predict to DFT, and Carsten has discussed this a lot. But as we can see here, so this is without correlations, of course, and we have heard correlations, and maybe Frank is going to talk about more today. So we can see at the Fermi level is very busy orbitals that we have, so occupied by combinations between nickel 3D and the 5D hybridized state. So it's dominantly the Fermi surface having this 3D x square minus y square. And then at the A point, so you can see this pocket of hybridized ND5 dxy and probably interstitial S state. So as well as at the center of the gamma point, you also have this ND 3z square minus r square orbitals. So if we try to relate to what we have observed from the transport, for example, so we have this Hall coefficient, so this might explain or somehow consistent with the having these multi-band structures from the DFT. So the idea of having self-doping, it might also lead to these differences that we observe between the cuprate and the nickelate. So, and that's also probably the reasons why we don't have this mode insulator parent compound. You know, as I said before, we have this weakly insulating behavior. And then there are many other experiments that I'm not going to talk today, but just to highlight. So for example, from the EELS and XIS absorption spectroscopy, it's kind of consistent also having this less hybridizations between the oxygen 2p and nickel 3d in comparison to a strong hybridization that we have in the case of cuprate. So this also leads to the idea that in the case of nickelate, we are, from the framework of the Zanen, Sawetzky, Allen, that we have this Mott-Hubbard framework rather than the charge transfer as in the cuprate. And from the rigs, for example, we do notice some kind of magnetic excitations, but there is no long-range order, and the coupling energy is much lower than what we have in the cuprate. So this, again, maybe something that have to be clarified, whether this is something to do also with the, for example, lower TC that we have. And then report on chart order that has been proposed by different groups. But again, here there is an inconsistency that needs to be further clarified. So what really the challenge from the experimental point of view, all right? So as I demonstrated before, all of those data simply based on thin film samples with a thickness ranging from 5 to 12 nanometer. And even for these samples, right, you are dealing with many different issues with crystallinity. You have stacking faults, secondary phases, and so on, that you really need to take care of before you can make a conclusions based on the experiment that you do. So there is, of course, no bulk single crystal yet that shows superconductivity, and the rate of that you can reproduce the sample is relatively low. Okay, and again, as you can see, there are only a few groups that have been able to produce. So it looks like to us that reduction is really the main issue, the removal of the apical oxygen, because we really don't have control in this way, in doing this one. So of course, this also creates issues with many experiments that we are not able to do, at least conclusively at this point, like RPES, NMR, and so on. So what we do in our lab is doing pulse laser depositions. People have done also using molecular beam epitaxy. And this is how our system looks like. And then this is will be subsequently followed by apical oxygen removal by calcium hydride soft chemistry reduction. And as you can see here, in terms of the perovskite structure, is perfectly fine. As you have this reed oscillation show that you have really layer by layer in the perovskite structures. So the surface of the substrate before and after the growth, and even after reductions, you can see this nice step of the STO substrate, which indicate, at least in terms of the perovskite structures, you should not have a problem in trying to reproduce the sample. So again, the problem looks like in the soft chemistry process. So ideally, what you will have during the reduction is the oxygens will start to be removed alternatingly, right? And then as you continue this process, and then you will produce the infinite layer structure, all right? So this is the thing that we really having a problem with. It's difficult to control. So ideally, it would be nice if we can really look into the oxygen state, the different reduction steps, even if we can do it real time, okay? And then Carsten has proposed the idea of the hydrogen issues in this nickelate as well during the reductions. So what SIs that we are able to do now is really based on three things. So we look into the so-called lower fringes in the XRD, and then using high resolution STM, we try to confirm. Of course, this is going to be a very slow process. As you are aware of, STEM is a very tedious thing to do. And then, of course, resistivity is another hint that we can really use to judge the quality of the samples, whether we are going to be able to produce superconductivity or not. So in the last few years or so, try and error is really the main thing that we are doing here. So hundreds of samples every month that you need to produce to be able to do experiments to produce superconductivity. And we have been playing also in doing different way of reductions process, trying to do a matrix, trying to combine between having a high reduction power as well as quality of the crystalline samples that you're going to produce. For example, this is probably a good hint for people who are also interested to do this. We have been trying to use similar approach as Howard Wang, and we have not been able to do the same. Process. The sample is not superconducting. So it looks like this is the problem. So you cannot really. So it's really have to be optimized with your own system, especially this reductions power of of this apical oxygen removal. So anyway, I'm not going to discuss this in too detail, just to highlight the sophisticated process that need to be done to really optimize your samples. So at least up to this point, we are now at a state much better than the initial samples. Oh, sorry. Where did I? Okay, maybe I point out here again, as you can see here, in the initial batches of samples, you notice there is no lower fringes. And this somehow associate with the high off-tilt structures, secondary phase that you have, and you only have this infinite layer up to probably around 5 nanometer, kind of a nice structures. Beyond that one is still, the density of this secondary phase is really large, as you can also see here, right? And this is from Howard Wang's group, so it's kind of consistent. Having no lower fringes is associated with a large density of secondary phases. Now, as the process has improved a lot, so let me call high crystalline samples, right, in a quote. So you can see the density is much lower with a very clear lower fringes. And of course, resistivity is also consistent with having superconductivity at the end. And this is also somehow consistent with Harold Wang's group. So this is what they call the high crystalline samples, and they also start to see these lower fringes. Okay, so these are the eyes that we are using right now to try to look into our samples. But just to point out to Carsten's point just now, claiming that this is a high quality sample is not really true, because in the previous sample it's also within 5 nanometer you always have a very nice infinite layer. While this sample is actually limited only to 5 nanometer. So it's not a thick sample. So that cannot really be said that for high quality samples in the case that you put this on the LSAT substrate. All right, so at least having this so-called quality samples, now we have been able to produce and also try to do different experiments. So the next 2 slides, I'm going to discuss 2 main experiments that we have done recently. So as you can see, again, the lower fringes quite a good high resolution TEM data, very relatively sharp transitions, and you can observe DC diamagnetic response directly from this sample, high quality sample. So one of the questions, of course, the pairing symmetry, and experiment has been done before by STM in a group of China. As you can see here at the different locations on the same sample, you see this V-shape or U-shape features of STM. So there are kind of mixed conclusion from here, either whether there is really an actual mixture of the symmetry or simply because of the inhomogeneity of the samples at the different locations. Okay, so because of the limited samples, what we are able to do so far is doing London penetration depth, is basically looking into the response of the samples as you apply magnetic field and the resonance frequency of the LC circuit, and this difference in the change of the resonance frequency will be proportional to the change in the penetration depth at very low temperature. So we have to aim at very low temperature, so millikelvin, 100 millikelvin. And this, of course, the London penetration depth will be proportional to the gap of the system. And you can look into the fitting and the power dependence of this one, then you can classify whether something related more to the D wave or S wave or the mixtures of the D wave or S wave. So as you can see here, so I only show 2 data here, but we have done very intensive analysis on this one. So none of them that show pure symmetry with a nodal behavior, right? So there is always some kind of not less features that have to be included in the fitting, okay? So we cannot really claim that it's a pure D wave, right? So in the case of lanthanum base, for example, there could be a mixture between between S wave and D wave, while in the case of ND base system, it's difficult to say. So in conclusions, what we can say, there could be this multi-gap that we have in the nickelate system rather than a pure D wave. So another interesting thing is the upper critical field. Harold Wang has reported before that there is this isotropic Pauli limited behavior in the case of the ND nickelate, and as well as the upturn at very low temperature, okay? But when we do this, especially in the system based on lanthanum, as you can see here, the Pauli limited is violated, okay? 3 times of the limit of the critical field based on the Pauli limited simple BCS idea, okay? While there is a slightly different features in the case of the ND, where we don't see this upturn as we really go down to a very low temperature, 10 millikelvin. So this violations of this Pauli limited behavior is really a tricky thing that we cannot really find reasons right now. Because if we look to the BCS, you So might have these violations, but it's not in a way that's similar to what we have. For example, you can have ideally you will have this Pauli limited one, both in the case of in-plane and out-of-plane applied magnetic field. So the out-of-plane magnetic field probably related to the orbital effect, while in the case of the in-plane can be because of the paramagnetic Pauli effect, okay? While in the case of this lanthanum nickelate, the violation is in all directions, okay? In all directions of the crystal axis. So you can have violation, for example, in one of the directions, which has been shown in the case of the tri-layer graphene, right? And this can be nicely explained by having a spin-orbit coupling locking your Cooper pair in one of in the plane, for example, okay? And there is also small violations that sometimes observed in the case of, for example, the multi-band iron-based superconductor, but never been seen that it is, like 3 times of the limit, the Pauli limit, okay? So this is something that we really struggling to understand and trying to do more experiments right now to really pinpoint the reasons for these violations of the Pauli limit of the critical field. So if we compare to the heavy fermion, for example, this is the only thing that we can see that there is this violation in all directions, which is significant. And this is, of course, the triplet superconductor, P wave. So whether this is something to do with this one is probably very, difficult. You need to really do, for example, the other experiments to confirm the reasons for these violations. Well, just to conclude now, there are differences, of course, there are similarities in the case of cuprate, but it's not just limited to the cuprate. We also notice this, in the case of the violations of the critical field, you need to learn more from the heavy fermion system, as well as this Moire graphene that kind of having some similar features. So more things that can be done, for example, to try to also produce system that is dominantly electron doped, right? In the case of superconductivity, as well as, of course, producing bulk superconductors, and then probably a new system without the self-doping that probably create differences with the cuprate that we observed so far to make it more pure, closer to what we have in the case of the cuprate. All right, so with this, I thank you for your attention.
Thank you. Any questions?
So you associated this weak upturn of the resistivity to Anderson localization, which is, given that it's a weak effect, quite reasonable. Have you or other experimentalists been able to prove this more by correlating the strength of the upturn to the disorder, or by applying a magnetic field, so that if it's Anderson localization, it should then go down the resistivity?
No, yeah, this is something have to be done, I think, yes. Thank you. That would be a good thing to do.
Any other questions?
I would just like to ask, is there any way to determine that the Fermi surface where the band crosses, okay, the Fermi energy, that it is oxygen dominated or nickel dominated? It is predominantly D wave orbitally or P wave?
Probably this, well, to my understanding is yeah, it's
no, but the
so there is
question.
still oxygen contributions, I believe. We observe this in the case of thickness dependent, where there is a change in the pre-peak before the main peak of the nickel, which is likely because of the hybridization between the 3D and oxygen. So I think dominantly is 3D xy minus y square with a small hybridization with oxygen.
Okay, thank you.
It's really a nice talk. I think 2018 we were also try to adopt the nickelate to see the superconductivity, but we didn't succeed. But it's nice to see your accomplish. My question about the phase diagram. You have a phase diagram on the dome shape. You have two hills, and
Yeah.
because of the transition from the electron dope to the hole dope, what I expect, there should be some separation. If we are talking about if it's similar to cuprate, and at the low, I think compensation of the carrier concentration, and then what I expected drop down to the TC, and then to see some kind of the Pissoudi gap or some kind of the correlation effect, and then again the hold up regime, then we can see another dome shape phase diagram. Can you just explain me why you have this kind of combine the phase transition?
I don't think there is a concrete proof that this is intrinsic things, the dip in the superconducting dome. And personally, I believe it's more like sample-to-sample quality variation still in this case. We have reproduced the phase diagram with a better quality of sample. So this one that I showed is really the first one. And we don't have that dip anymore. So it's really just a single dome. So there might be, I don't know, but at least there is no concrete proof that it is really the intrinsic things in this case of nickelate.
Any other questions? If not, we thank the speaker again.
Thank you. It's okay.
Our next speaker is Frank Neckermann from Ruhr University, Bochum. His invited talk title is Multi-orbital Perspective on Correlated Electrons in Superconducting Nickelates.
Yeah, thanks for the introduction. So it seems we're already a bit late in the session, so I have to speed up, bring this talk through. Carsten was already saying something about the specific, but I can explain something myself also. So let me jump into this very quickly, and I think I can. I think I can skip most of the introduction because you heard already a lot about the connection between cuprates and nickelates. So just that I want to make some more points that are close to my understanding and thinking of the system. So we know that for the cuprates, or at least we think that we can use a one-band model that was used in many studies. But as we heard also this conference from Neben and from Dennis, that oxygen equilibrium are freedom are important for cuprates. So if you look at this one-band orbital that connects to this one band, so to say, it's a like complicated orbital because hybridizes very strongly with oxygen. So of course we are still using a Hubbard model, but there are also newer kind of studies that more and more put finger on these aspects of multi-orbital and oxygen degrees of freedom. So there's work in the community going a bit more to looking into these complications of this orbital, as also was Carsten mentioning. Then if you go to nickelates, it was a long search in history to find superconductivity of cuprate kind also in the nickelates. But there are some complications coming quite easily because nickel usually prefers nickel 2+ 3d8 configuration, and if you dope the known insulated nickelates that we know, for instance, the cuprate sister compound 214 nickelates, then you get all kind of in-gap states, not nice metallic states, or you get also nickel oxide for the Roxol compound. So this is a bit difficult, and one has to understand very, very deeply these effects of doping in these oxides, to my thinking. Okay, so but then of course there was a lot of work, as I said, historically on these infinite layer compounds, because this has the cuprate-like structure. You pull out oxygen and they form this nickel 1+ state. Indeed, that was looked for, but we heard already that the magnetic behavior is quite different from the cuprate, so there's not a nice endophthalmic ground state, at least at stoichiometry, that's what people think, and it's still not found. Then there have been theory work where even before the Anisimov work, there was a nice French-Russian cooperation work with some quantum chemistry work, which already put a finger on this lanthanum nickelate in the infinite layer regime that is a bit strange to the other nickelates. It's kind not gapped, but it's not a good metal. This was still kind of Hartree Fock-like calculations, but still very nice in view already to these earlier times. Then there was this, as already mentioned, Anisimov work that put this into a cuprate context, but then there was the follow-up work by Lee and Pickett, who then claimed that there is, of course, this self-doping band that was highlighted there in this work, and also saying that nickel DZ square takes on quite some importance in this compound, although still from a DFT plus U static correlation scheme, but still saying that this nickel 1+ is maybe different to the cuprate analogon. Then I can go over this very quickly. We know that it's been found by the Stanford group and then also by Andrews group and some others. I don't go into this in detail, just putting my finger again on something. So we have the comparison of the phase diagrams. Here the nickelate, here the cuprate. They look similar. Of course, the gap have a bit different shape, a different extension, but so whatever you would say, I mean, broad contact, that looks very similar indeed. However, there are some differences in the sense that here we have a decent insulator, but then we have a pseudo gap phase that is found. It also still has some metallic transport, metallic-like transport. We often have, and it's complicated, but it's metallic-like transport, whatever. And here we have a nice metal firm liquid at the overdope regime. It's quite different in nickelates. Here, the weakly insulating at overdope, it's in the overdope region. This might change a bit, but still it's not as good, even if the newer samples as in the cuprate. So there's something else going on. And even more strikingly, in the low doping, underdope region, it's still super weakly insulating, and there's no kind of metallic or whatever metallic-like transport yet found. This could be true sample issues, but even with the new sample, this still holds. As you can see, there's not much conductivity there. So this goes back to this doping aspect, that putting holes into this nickelate might be quite different, might be much harder than compared to cuprates. And the other hole data was already discussed by the previous speakers. I also want to highlight the magnetic features. Again, I stated that the endothermic order has not been found. There's been indication of quasi-static endothermic order, spin glass behavior. Then there's been this nice RIG study, again by Stanford group people and associates, that find paramagnetic-like branches in this thin film layer. So there must be some magnetic activity, some local, some endothermic-like dispersion coming up. Although, of course, in these RIG studies, I cannot claim any signs of static magnetic order. But still, dispersion is nice, although the width is quite different. That is much more incoherent than to the cuprates. A very nice recent study from Jennifer Fowley, from the Triscons group, and Martin Suter from PSI and also Stanford. I think this is a very important work that they show that for all compounds, if you look at all compounds, stoichiometric or dope that we know are superconducting, there's still strong magnetic activity far away from paramagnetic region in the superconducting regime, meaning that there are still local moment, and importantly on the nickel sublattice. This is not a F magnetism. They claim really it's coming from nickel sublattice that has strong, not ordered, but short-range order spin class like whatever, but strong magnetic activity even in the superconducting dome. And that is, of course, very different to cuprates. Okay, so maybe I can skip that because I already told you that about this comparison. There we still lack single crystals for the nickelates, which is, of course, very, very bad because that would be a good thing to use much more techniques. The TCs of order of 10 may be different. Roughly stated, it's not quite clear what order parameter. Ayanda was saying that there are some issues that may be D or P wave. It's not quite clear. And I told you about these weakly insulating differences to the cuprates. So, of course, now I'm doing theory, so this is the busy political-like slide of all people working in this field. This is very heavy. We heard already a lot about it. Just let me go through it very quickly. The main concepts that are discussed are, of course, what Carsten was putting forward, that it's mainly cuprate-like, x minus y square. So many people are in this field that think that there might be some decoration, some issues that are not really cuprate-like are maybe coming from hydrogen incorporations or from defects, and this will be resolved in the future. Then there's this condo-based issue that people think it's condo-based. So Wu Zhengzhang thinks that it's a condo-like, heavy fermion-like coupling. There are not too many people in this group, but still it might have some relevance still. We have to see. Then there was early on the idea that it could be a oxide heterostructure effect, but that has been ruled out quite recently because there's not a 2-deck formed at the interface, but rather a reconstruction to resolve the polar issue that comes from the nickelate. And then, of course, there's a large group that claims that there's multi-orbital physics. Many people are in this group, and myself, I'm also in this group. And just going to this kind of putting citations or quotes to this. So Carsten was saying it's like the Occam's race. We should use the simplest thing that is available. Wherever I can put another quote, we all know the Einstein quote: you should do things simple as possible, but not simpler. So if it's not that simple, maybe we have to go further. So let's look what is known, because known is, of course, the DFT comparison. So we all show that DFT is a converged theory, so we should agree on. I mean, there are some small things because different bases. Whatever DFT we should agree on. If we don't agree on DFT, of course, we have a problem. So let us compare this a little bit, because again, that's what we should all agree on. And there are these two differences, that we have the self-doping band in the nickelates, which we do not have in the cuprate. And another important thing that I also want to put forward here is, again, that this nickel DZ squared is quite far away from the Fermi level, the occupied part here, in the cuprate compound, whereas it's quite close already. I mean, it's like minus 1 eV, it's not super close, but it's still already close on the DFT level. And furthermore, this actively hybridizes, is seen by these fat bands, into this self-doping band. So the nickel DZ square is already right from the beginning a vital player. We know, people who know cuprates know that the nickel DZ square was always a candidate to be relevant also in cuprate, but many calculations show that it's really not relevant when you dope it and it gets shifted down. But we will see that it's different when we go to correlations in the nickelate. So we use DFT, DMFT. I don't have time to go into this in detail. It's a large machinery, but it still has some choices and some thinking in it. So it's not just a button pushing thing. So we have to do something to think of. And importantly, as also Carsten was already mentioning, the main difference between Carsten's calculation and my calculation is that I include correlations on oxygen. So I put some self-induction correction. Could use any other scheme maybe. That is just a matter of choice. It works very nicely because it also gives some band narrowing to the oxygens, and it shifts to oxygens. So because I think that is important, because the system is in these late transition metal oxides, and it's not Mott Hubbard-like, and we have to include this. And this is the main differences, and also the main difference in the results will come from that. So let us look at, so we use value of U equal to 10. I can explain many motivations, but one motivation is that I think it's not so important to have a very subtle calculation, because also these calculations suffer from the efficiencies that we have at the moment. So we use for nickel oxide, we use 10 eV, and we use the same 10 eV also for all other nickel compounds that we've looked on, and we have published that it really gives good results for the whole series of nickelates. So that is our U value that we take, and we have the SIG correlation with oxygen, and J is 1 if it's not so important. But the main result is that, as Carsten was always saying, that whereas the cuprate is strongly charge transfer-like with a very small charge transfer energy of 1 to 2, the nickelate is not, is like a Mott Hubbard thing. And this is severe because now all the transport is mainly affected by this. We know Mott Hubbard system from the early transition metal oxide, where we have T2G systems, which are multi-orbital already. And that is fine. You put hole in, and the T2G do not hybridize super strong with the oxygens. Anyway, they are threefold. So there is the hole can propagate in this 2T2G for the earlier transition metal oxides if they're correlated or if they're also Mott insulating. However, it's quite different for the late transition metal oxides, where we have this kind of architecture where there's a direct hopping path across the oxygen in the EG system of late transition metal oxide. Because you want to put holes in there, the hole has to jump somewhere. It likes it because of Heisenberg principle, but it cannot easily jump to the oxygen as in cuprates and nickelates. So the transport will be blocked more easily in these cuprates, in this nickelate. So the hole likes to go somewhere else, and what is there? As you have seen, the nickel DZ square is closer. So that will be the story, but the bottom line is this simplistic kind of arguing that I just put forward. So this is a busy slide, but we did the calculation with cuprate, so overdoped regime, and we see this sunrise-like thing. So the greenish thing, the quasi-particle is composed of two kinds of nickel D and oxygen. Both have the same contribution, whereas it's quite different for the same level of doping for the nickelate. And that is understandable because, as we said, it's not charge transfer light, it's more hydride-like. So the oxygen has contribution, of course. It's not black and white, but it doesn't have a large contribution. And if you look at the orbital sector, we still see, that was Carsten and others put forward, that of course, even in the overdope region, it's mainly single orbital. So this orange-like thing that you could hopefully see here is the the copper X-minus Y squared at large doping, and that is the only orbital that is the front orbital is important. Whereas for the same kind of doping, it's quite different. The holes go here in this nickel D set square because that is energetically much more favorable than putting holes into the X-minus Y square when you have this more Hubbard picture. And this is then confirmed in the theory calculation by the K-resolved issue. And how does that cope with this angle integrated situation? Well, we shift upwards in hole doping this nickel D set square band that we were already talking about over the fermium in a flat band like regime, and this takes on all the holes, whereas the X-minus Y square is more or less inert. It has still a local spin, and that goes together with the spin activity, magnetic activity that we have seen in the experiment. It doesn't really like to get hole. It's more or less inert and remains a localized spin, more or less. And so how we can connect to spectroscopy? There have been early EELS experiments on this, which also said, okay, the holes do not go very likely to oxygen, but they're very, very careful, of course, because they couldn't say so much in that, but it's not like clear if they go to said it's going to some other, maybe non-X-minus Y, but it's not clear because they can't resolve at the moment. Then there's been this only ever photo emission at the moment available. Carsten already mentioned it, and Carsten had this nice fit to experiment, so I also have a nice fit to experiment, and you can then decide which one you like more, which is more relevant to your understanding. So this was the photo emission from the Stanford group of CX Shen, only angle integrated for praseodymium, and let's look only at a stoichiometric kind here. This orange curve, you see the peak is at -2 of the nickel D, and then we have the oxygen peak at -5, -6. And that was in 2022, and my calculation was at 2020. So that is the comparison. I took over this curve. I just looked for the height of the peak, but then I put over the curves. So the red curve is DFT plus sig DMFT with the correlation with oxygen. The blue one is the pure DFT DMFT with the same U. And you see the comparisons rather nice. So again, this red curve is the prediction 2 years earlier, and that is the measurement. And you see the peaks perfectly more or less agree with each other. As Carsten was already putting out, if you now go to the doped regime, that doesn't match so nicely anymore. So then we would have claimed victory and said, whoa, we have the story. But for some reason, this doped curve looks a bit strange because you have 20% holes, and there's not much shifting in it. It's not quite clear how that even goes along with the hole counting. So there's something maybe missing, or more work has to be done, both maybe on theory and also on the experimental side. But again, this is the first one, and that we desperately need more spectroscopy. So if anyone is here does it himself or herself, or knows somebody who's doing it, that is, I think, super important to have more spectroscopy, photo emission. Even angle integrated photo emission would be already very good, just to compare. So then we do, from this basic picture, let me speed up, we do a minimal modeling. We take out these 3 contributions that we think are important: the nickel X-minus Y square, of course, the nickel D set square, and some self-doping band that is always there, at least at the geometry. We do an effective 3-band modeling with some simpler than DMFT scheme, and we get the same picture. Again, let's just discuss this curve. So with doping, this is hole doping to the right. You see this nickel D set square catches a lot of holes. The occupation goes down, very eagerly catches the holes, as we have seen in the full-fledged calculation, whereas the nickel D set square remains more or less half-filled, more or less inert. It doesn't want to have, the nickel X-minus doesn't want to have many holes, at least not in that regime. Then we plugged in this we teamed up with Andreas Kreiser, and we plugged in this kind of dispersion into his machinery of doing RPA susceptibility, spin fluctuations, and this is a similar curve as was Carsten was showing. Here's our comparison. It looks a little bit better, I have to say, at the moment than Carsten's one, but that could be an accident of RPA or whatever. It's of course a bit more simple than what Carsten does, but the agreement, at least again, also on this level is rather fine. Then we looked with this RPA spin fluctuations, we looked for the instabilities of superconducting kind. And interestingly, it strongly depends on the renormalization within the RPA. You know, in RPA, you need some renormalization, again, the RPA renormalization. And if we weakly renormalize within RPA, we get the same X minus Y square instability, even if this with this flat band incorporated. However, this switches with this correlation parameter. You see this is the leading order of X minus Y square kind, but then it's popping up two different instabilities, triplet-like and S plus minus-like. And triplet-like, that would go along with Ariando's finding, that indeed there could be some triplet instability. That could connect to this flat band, which maybe more tries ferromagnetic spin tendencies, and that is maybe more closer to a triplet instability. However, we think that with an RPA, it's hard to decide. Again, also triplet needs usually more vertex corrections, which are of course not included in RPA. So we, in this work, we still favor the S plus minus, which would also be nodal in our case. Okay, so this is the very quick summary on the infinite layer ones, kind of this phase diagram. So that interesting, there are various regimes coming up with doping in our calculations, and that as stoichiometry, there's still a Kondo-like feature. We had this upturn that was also mentioned by Ariando. I didn't talk about this now because it's a bit more involved, but we see like a Kondo effect of this mod insulating extra minus Kreisker band, which we have seen is rather mod insulating at stoichiometry. Sorry about this. So, but then we have this flat band picture when we go to the superconducting region, and then we have even more some mod Hund physics in this weakly insulating, and we could explain this weakly insulating behavior is seen in the overhead region by these Hund-like correlations of this two orbital kind of this flat band coming up and the X minus Y square spin. So that is a different regime. So so you could say this is like a bit Nick-tight kind of. This is a bit more Kubrick kind of, although not supercharged transfer. They meet in between with this flat band scenario giving rise to the superconductivity. If I have a few more minutes, I can also extend a bit to this multi-layer compound. So this was already put forward. If we go to the multi-layers, which can be more easily produced in experiment, if we raise the number of layers, we come from the overdoped region and enter the superconducting dome via more and more layers. And we did calculations on this. Maybe let me skip this, which is for the 3-layer compound, which is a bit of different physics. But maybe on my last slide, just to conclude that in more or less in good time, look in this 5-layer compound with the same machinery. And the main message here that we again see this nickel dz square like flat band. We have some X minus Y square dispersions, but they are far from the arc-like structure as we know from cuprates. So again, we have a shifting through of this nickel dz square, and that is really translating well to the infinite layer kind, whereas for the 3-layer compound, very quickly just to get a story photo. For the 3-layer compound, this flat band is above because we're already much more in the overdoped region, whereas for the 5-layer, it's right at the Fermi level, and this triggers then also the superconducting instability. But the coherence scale is much lower. Also with temperature, you have to go to super low temperatures from the BMFT sense of point of view to get coherence, and this maybe goes along also with this high fluctuation regime in the 5-layer compound from Julia Mundis group. But again, all this field is still at its infancy, I would say. Much has to be done. And there's some controversy, as we have learned, between Carsten and myself and also other people. But I think it's not bad, it's good, because it pushes the field forward and it motivates people more to do something. Everybody would agree. That would be maybe too simple right away. So that is nice, and we have just to see. And we also see that different theories give very good agreement in some parts and maybe worse agreement in other parts. And this is also from cuprates. I mean, some theories give super agreement for some measurements and completely fail for other measurements and vice versa. And we just have to select out and find if there's a common concept that one theory can cover all. And we also have to be careful if we have super good agreement, like in my case with this photo emission, or in Carsten's case with the dome, just from one experiment or from one probe claiming that this is now the perfect theory, because there could be accidental agreements which could lead you in the wrong track. So with this, I would like to finish and open for questions. Thank you.
probably to Alessandro. I mean, since these thin films exist, why is the problem to make ARPES on them or spectroscopy? Whoever wants to. I know, but this is kind of feasible in many other cases. And the interest is big. You have this also suitcases, with ultra high vacuum and stuff like this.
Let me please summarize my understanding of nucleates, and if anybody present disagrees, not just the speaker, please say. My understanding is that even though the nucleates are structurally similar to the cuprates, they are in fact more similar to the pnictides electronically. And the main reason for that similarity is that there is the oxygen ligands are much more passive in the nucleates than in the cuprates, so it is similar to the situation in the pnictides where the metallic conduction occurs directly from iron to iron, and the phosphorus ligands are passive. Okay.
Yeah, you could put it this way. I mean, I would not claim that they very strongly resemble a pnictide physics, because pnictides are very special. There's like multi-orbital, you have the full iron D shell, and the pnictide arrangement is also a bit different. But it goes a bit in the same direction as the role of oxygen is different. That I think I would agree on, and really putting a finger on that the charge transfer physics we have in cuprates, which I think is very, very important, and that has been a bit put under the rug with doing, especially I have to say from theory, with putting it on the Hubbard model level. Well, you can do the Hubbard model, but you always have to be aware it's not, it's not, again, the lattice is not copper, but it's copper, oxygen, copper. So there's the oxygen between, and we have taken out this oxygen very quickly. So there's always this oxygen between, and we have just taken it out and said it's like a one-band system, and that is, it works, but maybe for some accidental reason it works. And in the nickelates, this problem just jumps in your face, because there things are in the sense similar, that the role of oxygen are very subtle and crucial, but one cannot more easily put them under the rug, at least from my point of view. And again, as you said, the role of oxygen is not so important in some sense that it's not of charge transfer kind. So the holes do not want to go to oxygen. That is true. It's still important in setting the energy scales and the hybridizations nicely. And then it's different from the cuprates, where we have this strong linking. In my view, it's a bit, the nickelates are a bit a coupling of two systems. So you have the in-place system of XMS Weisskor and oxygen, which forms like a strong interacting entity. And then you have this nickel D set square hopping to the rare earths, which are like weakly correlated. So those two subsystems, they talk to each other in a very complicated manner. And this kind of two subsystem entity we don't have in the cuprates. So that is a bit my point of view.
The mass announcement of 25 is for that disease square band.
Oh, there's 20. Well, this was for the okay. You wanna go to
your last slide? You had like MSAR-RAM.
That was
25.
for the 3-layer compound. So that I skipped. Yeah. So this is
for
a
the 5-layer was.
No, this was for the for the 5-layer. Yeah. So this is the issue that comes out. For the 5-layer, as I said, the Korean scale is very low, so I would not claim it's not saturated at 30. I did a calculate at 30K, and it's not quite saturated. But even for maybe let's go to the 3-layer compound, where it's already very high, and there it's more or less saturated. But it's very highly correlated, the 3-layer compound, whereas in the infinite layer, at stoichiometry, it's in my case mod insulating. So maybe thanks for this question, which I didn't really put very strongly to everyone's mind. I think that these oxygen correlations bring in a boost to the correlation. So in Carsten's calculations, they have a randomization of 4 to 5, which is still good or strong, but are not really super close to mod criticality. Whereas in my calculation, you're close to mod criticality for x minus y square. And this translates then to this outer layer compounds. And there has been photo emission on this system from the Dan Dessau group, and they see from photo emission a value of 5, which is still large, I think, from other DFT, DMFT calculations. But then I would claim, if you look at specific heat in a related paper, this may be a longer discussion, we can discuss this afterwards, but there are specific heat measurements, and they, if you look at this gamma coefficient of specific heat for this compound, it's way larger than this 5, really going to this modest, to this 14, 12. So there's still an ongoing thing. Again, we need more spectroscopy. There's not yet photo emission on the 5-layer compound, but in my calculations, even more strongly correlated, but not fully coherent yet. But I think this is the main thing. I mean, all these transport measurements that we have are very nice and beautiful, and also these thinkings of which kind of order parameter. I mean, it's all very important, but I think it would be very good to first understand the normal state. Is it one orbital or is it more orbital? That would be, if we have settled this, we can go on with all these more detailed things. And I think that is very important.
Typically this kind of discrepancy between specific heat and ARPES means multi-orbital. Typically specific heat is very sensitive to what happens at exactly at the Fermi level, where ARPES, these factors in ARPES are
so we have this mix in of this nickel DZ square, although the whole this flat band is out above, but we have a mixing of this nickel DZ square. So they don't see this in ARPES. I talked with Dan Dessau in a long time, but it's ongoing work, so to say. I don't want to judge experimental measurements. Okay, who's the first? So we have to move. Thank you. Excellent, thank you. I think we are both sharing that. I did just.
Yeah, it's now 11:44. So in principle, the coffee break already is over, but you have the pleasure to take a coffee, because, as I just learned, the first speaker of the next session is not there, and we will then reconvene at 12:10 with a talk by Gabriela Aurelio. Thank you. video from Zaragoza and at the same time also from Argentina. So we are very much looking forward to this.
Thank you very much for your presentation and for the opportunity of giving this talk here. I am a little off topic with the things that have been being discussed in the conference, but in the end, I think that we have a common goal, that is to look for systems where we can tune. So as it was said, I work now in Zaragoza, but I'm only there for a sabbatical year. My permanent position is in Argentina, where I work for the National Atomic Energy Commission at the Laboratory of Neutron Beams. So I will present results on neutron diffraction experiments on ferroelectric polarization. So other interesting features of this crystal structure is that it is one of the very few compounds, oxides, where you can find the magnetic ion inside a purely tetrahedral environment. Usually you find octahedra, and you find a mixture of tetrahedra and octahedra, but a purely tetrahedral environment is difficult to find, and this compound presents that. And in addition to that, it presents, I will show you later, a geometry formed by triangular layers or Kagome layers, which lead to a strong frustration of the very strong antiferromagnetic interactions between the cobalts. So something very interesting happened when, instead of using a 3+ cation in this compound, a group in France 10 years ago tried to put calcium, which is a 2+ cation, instead in the place of the R site. And when they did that, contrary to the other compounds, a strong magnetic signal appeared below 60 Kelvin, and this is a ferrimagnetic order. And concomitant with that transition temperature, a strong signal in the dielectric constant measurements, indicating a very strong increase of the polarization. So this compound is not strictly, you don't have a reversibility of the polarization signal, but what you have below 60 Kelvin is an increase in polarization, which is triggered by the magnetic transition, as you can see here, because as you apply the magnetic field, you can see how this change in polarization achieves a value at low temperature that is indeed very high for pure multiferrics. So the origin of this magnetoelectric coupling is supposed to be in a magnetostriction mechanism, and I will, well, I am signaling here the value of this jump. What I will be showing you today is what happens when you start playing with this 2+ cation at this site of the structure. So we replaced calcium by strontium, and we prepared a series of samples. We could achieve the highest level for pure samples was 7 atomic percent strontium, because if you go higher, you start to segregate strontium. So we did very careful measurements that we were putting strontium really at that site, and that the samples were pure. And the first characterization of the system was the magnetic measurements, and we immediately can see that the effect of adding strontium is quite impressive. There are a lot of things going on here when you start adding strontium. So the parent compound has this typical ferrimagnetic type of behavior, but already for a 2%, which is the orange curve, and 5 and 7%, you start decreasing. Here is a logarithmic scale in the magnetization. You start decreasing this magnetization, and also you start introducing these kind of behaviors with an hysteresis here and a plateau, which I highlight better in this figure. You can see that there is a region between 62 and 82 Kelvin approximately, where something else is going on, and the magnetization starts to get flat. And in that region where it gets flat, you have some features in the specific heat. So there's something going on there, and we wanted to see what was happening in this region. For this, we did Newton diffraction experiments. So in order to see the difference on what was going on in that temperature range, we needed to first be sure that the low temperature state was as expected, and what is as expected. This is a measurement for the pure sample with no strontium, and this is a measurement for the 2% strontium sample. And the refinement is done using the Rietveld method with the full program, and taking into account, of course, the magnetic contribution to the diffraction pattern. For this, we use the formalism of magnetic space groups. And the space group in this case is indicated here. And you see that we have a propagation vector for the magnetic structure, which is 0, 0, 0, which means that the magnetic cell is the same as the crystal cell. And the system is indeed very magnetic, and it shows a net moment along the A-axis. If you do a plot of this structure, here you have the compound, and I've just removed all the atoms except cobalts, and I've put different colors for cobalts in a layer that is a triangular layer, and a pink layer that is a Kagome layer. But you shouldn't think this as a layered structure, because actually they are coupled. And in the cell, there are 4 different cobalt sites crystallographically, different weak of positions, let's say. So this is a view from above. You can see here the triangular layer. These are cobalt 1. They are further apart. And then you have the Kagome layer on top, if you look it from the Z-axis. And you have the 3 remaining cobalts in the cell. And the magnetic structure is quite complex, but you can think of it as, I don't have enough contrast here, but you must believe me that here you have a zigzag chain running that way along the A-axis. And in this zigzag chain, they are coupled ferromagnetically. And then you've got the triangular cobalts and cobalt 4 that are also coupled ferromagnetically between them. So this gives a net moment only along the A-axis. So if you have a look at the strontium with 2% strontium doping, the diffractogram looks quite the same. And so we focused on this region, because here is where the magnetic signal is higher, and you can see if there's something going on in the magnetic order. So for this, we did thermodiffractogram experiments, which means that you vary temperature as you collect the diffraction patterns. And indeed, even for only 2 atomic percent strontium, we did observe that there was something going on between 62 and 82 that manifests with this peak and this other peak here, and some other small features. But indeed, the white arrows indicate the ferrimagnetic phase, and this is another phase that is different. So what was this second phase appearing there? We also measured the 5% and the 7%, and we observed that there were some common characteristics. We tried to fit that with the Rietveld refinement. And when you try to do that, the first thing you look for is a propagation vector to see how the magnetic structure correlates with the crystal structure. And in this case, we found an incommensurate phase, which means that you have a modulation with a very long modulation period. This is 510 angstroms along the Z-axis, and antiferromagnetic along A and B. This is the propagation vector that we find, and we could fit the 3 samples data with this model. But which is the model? You have to find or to propose a model for this magnetic structure, not just a propagation vector. To do that, using Newton diffraction, one strategy is when you are dealing with incommensurate magnetic structures, which are the hardest to deal with, we used the superspace group formalism, which is very recently implemented in FullProf from 2020. And you think of the magnetic structure as a basic structure with a conventional magnetic group, a Shubnikov group, and you add a modulation function with a propagation vector k, which is the one what we found from the data. When you write the magnetic moments at each crystallographic site in this way, then you can inject this into the foolproof program and make a refinement of the directions and the moduli of the magnetic moments at each site. And when we did that, we obtained a model, a magnetic superspace group, which is this one. And let me show you. This is the modulation of the magnetic moments at each site. And you will see that in the triangular sides, you have not only a modulation of the strength of the magnetic moments, but also a rotation, an helical rotation of the moments. And at the Kagome sites, you only have a modulation of the amplitude of these magnetic moments. So this is quite a complex structure, but it is not so surprising because of the strong frustration that this lattice presents. This is the first time that this plateau in the magnetization is explained in terms of a magnetic model. It had been observed in other systems where the substitution site was not cobalt, calcium, but cobalt, for instance, by replacing cobalt with zinc, by replacing cobalt with aluminum or other cations. They also observed a plateau in the magnetization, but there wasn't a model proposed for this phase. So this is the first big result that we got from these substituted compounds. Sorry, the other way. And as I mentioned, you have different modulations depending on which layer of the structure you are looking. But next, we had a look at what happened below that phase, below 62 Kelvin approximately. So first of all, if we have a look at the lowest doping level, you need to obtain at the lowest temperature the ferrimagnetic structure that I showed you in the beginning. But what happens in the middle between this incommensurate phase and this ferrimagnetic phase? And in the middle, what we observe is that the incommensurate phase locks to a commensurate propagation vector. Okay, great. This propagation vector is now 1/2, 1/2, 0. So you lose this modulation along the z-axis. And the difference between both models, if you compare them, it is quite difficult because they are complex structures. But the main difference is that the ferromagnetic coupling that we observed at low temperatures between these two cobalts now turns antiferromagnetic. So all in all, this structure does not have any net magnetic component, but you need to remember that the Newton diffraction experiments are done at zero field. You don't have any applied field. As soon as you apply some magnetic field, this can change completely. So this is something to have in mind. Another thing that we observed and is indicated with these black arrows is very tiny additional peaks. These peaks are of a magnetic origin, and they are not accounted for by any of the models that I have been discussing, nor the ferrimagnetic one, nor the ferrimagnetic one, nor the commensurate antiferromagnetic one. And so we call this a second additional incommensurate phase because if you try to index the position of these peaks, they are compatible with a propagation vector that is also incommensurate. When we increase I'm just finishing here, when you increase strontium content to 5 and 7, what you get is that you keep this commensurate 1/2, 1/2, 0 phase all the way down to Kelvin, 1.5 Kelvin, and you also keep these additional small peaks that we can't find a model. We can't find a model for these peaks because they are very tiny, and we are immersed in a very complex phase already, so it is not reasonable to obtain a complete model for these peaks. But they are there indeed, and they are there in the 3 samples, so something is definitely going on. And we think that this is strongly related to what happens when you increase magnetic field. In the magnetization, the increase of the magnetic field applied has a strong effect also in this hysteresis and the coexistence of these phases that we are observing. So the other way. So to sum up, as I told you, it had been repeatedly reported in the literature the effects of doping and the destabilization of this ferrimagnetic phase by substituting mostly the cobalt site, but not other sites in the structure. So we present results for the substitution at calcium site. The strontium addition really favors complex antiferromagnetic arrangements. We proposed a model for this incommensurate phase. And we also propose a scenario at low temperatures where there are two phases in coexistence, two competing phases. One is 1/2, 1/2 zero phase, but we also observe additional peaks that can't be accounted for by these models. And this highlights a very complex energy landscape and the possible role that magnetic field could have on this balance of phases. And thank you for your attention.
So these are very frustrated layers. You said also that interlayer coupling is relevant. So for the Kagome, I wouldn't even know what kind of order I would expect, but for the triangular, I would expect this 120 degrees ordering. But that would be 1/3, 1/3 zero,
yes.
right?
Yes, and that doesn't...
Do you have any understanding why you get another ordering wave vector?
No, the first guess, of course, was to look for the 1/3, 1/3 zero because this is expected for this kind of triangular layers arrangements, but that didn't fit the data at all. So we said, okay, we have to expand our search for the propagation vector. So I think that the interaction between the layers is playing a significant role, because if they were isolated, you would have that order for sure.
Thanks.
So I have like maybe you mentioned this and I missed it, but you started discussing this material from the context of the magnetic phase, which you extensively described, and then you also mentioned that there is like a polar phase.
The structure, the crystal structure, yes, is a polar.
Yes. Yes. So it's in a polar group. Let's say,
yeah.
While all of this is happening, and is there any reason why, like, or is the connection between these two things are completely decoupled? You are only thinking about the magnetic part, and
I am studying the magnetic part because I'm using neutrons, but the possible origin for this coupling of the increase in polarization that you observe if you measure the electric constant, or if you make experiments of polarization, this is probably the origin of that is magnetostriction, because I didn't show it, but the ferrimagnetic phase has a very sharp change in the lattice constants, a stepwise change in the lattice constant. And this step disappears when you start doping. So that really sharp magnetostriction phenomena is driving probably the increase in the polarization, which is always there because of the polar nature of the crystal space.
But beyond that, there is no like a strong effect on what kind of magnetic structure you expect, or how it will evolve?
No, that we have found, and as soon as these other phases start to emerge, the polarization is not so, the increase is not so big. So it doesn't go in the direction that we would like for, let's say, for applications, but I think it contributes to our understanding of the stability of the system. You have slightly different models. I think I went very quickly over that. But charge order was proposed in the first publication of this structure, but it was based only on a difference of interatomic distances, and it was not very robust. Some years later, people conducted more precise synchrotron radiation measurements, and they show that you really can't justify a charge ordering scenario. So I think we're here. You can see that there is a difference between the strength, the magnetic moments, but you can't really say that it's charge order. Okay, thank you. Yes, sure. Thank you very much.
So we have the online talk of Munna Brahman from Islamic College Peshawar in Pakistan. Are you there? Can you hear me?
Yes,
Okay.
I'm here.
So take it away.
Okay, thank you very much. Can you hear me? Hello?
So your talk is also 20 minutes. We try to give you a sign by hand when you reached 3 minutes before the end of your talk.
Okay.
If possible. Otherwise, we
Okay.
go to control.
Can you see my screen?
Not yet.
Now it's okay?
No. Did you give
Why
proper
it is
rights
not?
for sharing the screen? Okay. So then you should go to the green button at the Zoom and select share screen.
Where is green button? This one, share screen. Yeah, okay.
There is something happening. Yeah, we are there. Go ahead.
Okay. Okay. So you got my screen?
Yes.
Okay. Thank you. Hello to all, and thank you very much, and good afternoon, because here in Pakistan it is afternoon. So the topic, and I'm thankful to the conference organizer who provided me opportunity to present my work, which is about the sensing mechanism of a material. So the topic of my presentation is electrical and aesthetic properties of Lofen compound based on sensor for industrial and environmental monitoring. And I'm Professor Dr. Munibur Rahman, Chairman, Department of Physics at Islamia College, Peshawar, KP. Province name is KP, and I'm living in Pakistan. So what is humidity? Humidity is actually the presence of water vapors in air. And why we monitor this humidity? Because it affects the human comfort and also various physical and chemical and biological processes. And also it increase the cost of industrial products. So that is why it is important to monitor humidity in the environment. Either it is in labs or in industry or in food industry or a textile industry. So that is why to monitor the humidity. So we need a humidity sensor for it. These are the different industries and semiconductor industries and medical applications. Similarly, in agriculture and domestic applications, these sensors are usually used. Relative humidity basically is defined as the ratio of actual moisture present in the air to the highest amount of moisture present in the air at that temperature. So we usually will talk about the relative humidity in my presentation. So these are some disadvantages, or you can say that why humidity is monitoring is necessary. This is a bark painting which is split after drying out in a low relative humidity environment, and the photo courtesy is going to Art Lab Australia. So this is this bark painting is split due to the dryness present in the air. So that is why relative humidity monitoring is important to protect our precious values, our antiques. So these are some other industrial applications. In insect usually generally like a warm damp environment, and it due to which it grows and destroy the products. Similarly, corrosion also promote in damp environment, and similarly the discoloration in textile industry also due to the relative high humidity environment. So that is why to protect or valuable items, so we need monitoring of the humidity in the environment. So we fabricated the capacitive type humidity sensor, and here some advantages and disadvantages of capacitive humidity type sensor is presented. These advantages are that it can withstand below temperature of 0 degrees C, and the next advantage is that it does not require any maintenance for longer period, and it is also flexible to use. Atmospheric, it is independent of atmospheric pressure, and it work when pressure is being applied. The disadvantages are it has limited long-term stability, and it is very sensitive to the diving and certain aggressive substances, uh, and it is usually also a bit less stable due to this organic compound, so it degrades with time. So the current work that I'm presenting is based on this paper that we published in Materials Today Communication, with a title Electrical and Aesthetic Properties of Organic Compound Based Humidity Sensor and its Dualistic Interactive Approach to the H2O molecule. So how it sense these materials, this low-pin compound or organic compound based humidity sensor, how it interacts with the water molecule. So this is a olefin compound, and in the central ring, which is a imidazole ring containing N site and NH site, and the water interact dualistically at both these sites, and due to which the resistance and capacity, humidity and sensing, because the dielectric properties of the dielectric constant of the water is almost around 80. So when the surface, when we introduce this surface to the humid environment, so the water molecule get deposited on the surfaces of this needles, and it also percolate into the voids and pores channels inside the surface. So more and more water will be accommodated by the surface. So the electrical properties in terms of capacitance and resistance of the material change, or we can say that the sensing properties of the material is changed. So this is basically the setup that we use that basically this is the setup that we use for humidity measurement. This is you can see on the right, this is a distilled water tank, and this is a dry nitrogen cylinder, and these are the valves which are open to increase the humidity on the left side, where the sensor is placed in the chamber. So we increase the humidity inside this left chamber by purging this nitrogen, and this water vapors comes to this testing chamber in which the sensor is placed. And this sensor is the humidity is monitored by hygrometer, which is connected with this chamber, and similarly this sensor connection is taken and is connected with the LCR meter, through which we can measure the note the capacitance and resistance of the device with the increase of the humidity inside the chamber. This is the results of the capacitance at different frequencies. We increase the humidity from 45% RH relative humidity to 95% RH. We can see that at low frequency, at 1 kilohertz, the capacitance of the device changed from 11 picofarad to 460 picofarad at this applied frequency of 1 kilohertz. So we see that as the humidity is increased beyond 65% RH, the capacitance is abruptly increased to 460 picofarad, and then we change the frequency to 10 kilohertz, the external applied frequency. We see that for the same humidity increase from 45% RH to 95% RH, the capacitance of the device has been dropped to 18.9 picofarad, though it is increased from 7.29 picofarad to 18.9 picofarad, but at 95% humidity, if we compare at 1 kilohertz and 10 kilohertz, so the capacitance of the device at 1 kilohertz was 460 picofarad, which is dropped to 18.9 picofarad at 95% RH. So there are there is also general rule in solid state physics that at low frequency, all polarization effects contribute. For example, ionic, atomic, orientational polarization, space charge polarization. So all these polarization contribute at low frequency. So that is why at low frequency, the capacitance in 95% RH was increased up to 460 picofarad. But at higher frequency, 10 kilohertz, usually the orientation, the ionic molecular polarization are seized out, and only electronic polarization effect is remain and contribute to the overall capacitance. So that is why at high frequency, this bluish line, we see that at 95% RH, the capacitance is reduced to 18.9 picofarad. This is the resistance of the device with the increase of relative humidity in percent. So we see that in both cases the resistance of the device has been decreased. The reason is that when in the imidazole ring, due to the N site and NH site, it interact dualistically to the water molecule, and due to autoionization of the water molecule, it split into OH ion and H plus ion. So uh, we can see in the next few slides that how this conduction mechanism occur. This H plus ion moves half and moves toward one plate, and OH ion, which is negative ion, moves to the other plate depending on the polarity. So due to water molecule, we see that the resistance is initially at 45% relative humidity, the resistance is high, and it decreases gradually. But when we increase the humidity inside the testing chamber where the sensor was placed, the resistance of the device is abruptly decreased because at 65% RH, whole surface of the sensing material is covered uh, by interacting or we can say that the water molecule are absorbed chemically. Yeah, it is chemized. So this below 56% RH, the surface is uh, only covered, and this mobile, this is less mobile molecules which are attached chemizably to the surface of the material. So it is less mobile. That is why the resistance is high up to 65% RH. After 65% RH, beyond, if we increase beyond, increase the humidity beyond this 65% RH, the resistance decreases abruptly. The reason is that the water molecule, uh, uh, when comes to deposit, so it absorb in physics fashion. So the water layers are added up in first and second and third and fourth and so on physics layer. So the H plus ion and OH ion are a bit more mobile in physics layer in the bulk liquid. So that is why the resistance of the device is abruptly decreased beyond 65% RH.
Just to give you a
This
time
is
stamp.
Okay, this is the water molecule and dualistic approach of the water molecule to the central imidazole ring at N site and NH site. This is how this conduction mechanism occur. The H plus ion interact with water molecule and it forms the hydronium ion. This hydronium ion then interact with the next neighbor water molecule, and it promote its H plus ion to that molecule and it becomes hydronium ion. And similarly, this hopping mechanism is going on, and we call it a Groth's mechanism of conduction. So this is a temperature setup, measurement setup, and this is the resistance with temperature, how the resistance of the sensor is decreased with temperature. And this is the response and recovery time. So quicker the response and recovery time, the more is more quickly we can use for the next measurement, the device for the next measurement. So in this case, we noted that our response time was 39 seconds, and the recovery time of our device was 20 seconds. This is the hysteresis loop of our device, which shows a narrow hysteresis loop. And for idealistic device, the loop should be at least minimum. The hysteresis loop should be minimum. Our hysteresis should be at least minimum. So this is the sensitivity of our device. At 1 kilohertz, the sensitivity of our device is quite high, above 70% RH. This is the conduction mechanism, and this is the curve fitting. We see that this at lower relative humidity, the capacitance increases very gradually, but above 60%, we got another slope of curve in which the capacitance increase abruptly. So this is because of the first chemizab layer in the low humidity region when the surface was covered with the water molecules. So the next layer deposited on this water molecule, chemisorphed water molecule in the physisorption and second physisorption, and in that case, in that in those physisorb layers, the H plus ion and OH ion migrate very quickly. So that is why the capacitance of the device has been increased abruptly. This is the stability of our sensor, and we tested it for at different humidity level for different days, and we see that almost the stability is quite good of our sensor. This is the comparison of our result with other reported results available in the literature, and we see that this low pen compound having response time 39 second and 20 second is quite good in comparison to the SNO2 material which is used for sensing mechanism, whose response time was 120 second and recovery time was almost comparable to our results. So similarly, there are some other materials which have better response and recovery time than our case. For example, SeO2 have 10-second response time and 3-second recovery time. So CEO2 is response and recovery time is good as compared to our other one. But mostly we see that our results are quite good than the rest of the materials which are used for humidity and humidity sensing. These are the references used for in this presentation. And thanks a lot for your patience to listen my talk. Thank you all.
Professor Rahman.
Yes.
The paper is open for discussion and questions. Yeah, Frank?
Yeah, so maybe a very short question. I don't know if I understood it correctly, but you nicely separate these different regimes of physisorption and chemisorption. Did I get it right that you could influence that or tailor that with frequency, or is there any other way that you could, if it's materials dependent, or to change the different layerings, which are those? Could you extend the chemisorphed layers to beyond one layer, or is that just a picture? Maybe you could say a bit more to that. Thank you.
So this is basically the capacitance of the device, and we can see that the goodness of fit R square is 0.98. So when R square is nearly equal to 1, so it means it almost gives you a linear behavior. So linear behavior means that actually the data, it gives you the actual data. So we see that there are two regions. The first region, we see that on the left side, if you see the surface of the material, which is shown in the same image just below. And then the water molecules, when we increase the humidity from 45% RH to 65% RH, so this surface and voids and pore channels are covered by the water molecule, and it interact chemical bonding occur on with the material at N site and NH site that I showed the amidazole in the amidazole ring. So it is less mobile layer. So the H plus ion and OH ion cannot easily move from one plate to another electrode, from one electrode to another electrode. So that is why the capacitance increase is not that much pronounced. But we see that above this on left side, if you see the cartoon, above this first chemisorb layer, the water molecules are just sitting on the surface of this chemisorb water layer. So it interact with the water molecule and it absorb in the physisorb fashion. So similarly, other water layers are added up, and in the above layer, this behaves like a bulk liquid. So in bulk liquid, and due to auto ionization of the water molecule. This H plus ion and OH ion, this will facilitate the motion of the H plus ion and OH ion, and that is why the capacitance above 65% RH is enhanced abruptly when we increase the humidity level inside the testing chamber beyond 65% RH.
Okay, thank
Yes.
you. Other questions? So maybe I could ask one. I'm not an expert on humidity measurements at all, but if I understood your experimental setup correctly, so your x-axis here on the slide has been measured by a commercial humidity meter, and how is humidity measured in such a device actually?
So if you see this experimental setup, this is this one. Okay, so on the left side, you can see that this is a humidity chamber. This is a humidity chamber, and the sensor is placed inside this humidity chamber. This is why we call it humidity. This is a simple chamber, but we want to increase the humidity inside this chamber. So we call it humidity chamber. So actually, we want to sense this humidity, water vapors inside this chamber through this device that we made
so my
locally.
question was actually to the lower left humidity meter, which goes into your chamber, and which I suppose is your x-axis, lower left, to the left of your mouse pointer.
This one, this one. So this
that
is
the
this.
commercial one, I guess. And how is
Yeah,
humidity measured
oh
here?
yes, this is the humidity meter. That is why we increase the humidity of the this chamber. We want to note the humidity.
My
How we
question is
increase,
just
how
how
the
this humidity meter, which I think is commercially available, is humidity actually measured?
yeah, but it is on some other material, based on some other material.
Okay.
So
And you know
yeah,
what kind of material and
yes.
okay. If there are no further questions, I just learned that the last talk has been cancelled. So let's thank both speakers once again of today's session. And I think then we have now the lunch break, and in the afternoon the excursion.
Thank you very much.